We'll proceed on calculus, algebra, and gradient vector. So we have already seen calculation of the gradient vector as far as the parametric vector is concerned. So there we have kind of calculated the gradient vector when it is a parametric when it is a parametric vector. So in that situation we have kind of calculated the okay, so in that situation, we have calculated the uh, gradient vector when it is a parametric vector. So one side, two side that we are consistently seeing. One is one side is parametric vector side, and other side is algebraic side. We should have started with the algebra easy part, and then we should have tackled the parametric vector, but somehow we did the other way, and we took the parametric vector first. And when we have a kind of line, surface, or volume, and for that if I have a parametric vector is nothing but a vector which has single independent variable algebra. Okay, so if I say I have a function called fxy, then there the fxy is an algebraic function with two independent variable x comma y. Fxy is two independent variable function. Those independent variable are xy. If parametric equation is a single independent variable algebraic vector equation, then there is only one independent component is called t. So if R is a vector, then parametric vector is R. Now R is a vector and function both. R is a vector and function both over T. So R on top of it, if I say arrow, then it becomes a vector. But if I say R and in braces, if I put T, then R becomes a function over independent variable T. If I combine these two, R on top of it, there is a vector sign and there is a braces and there is a T down the line inside it, then it becomes a parametric vector. A vector with algebra, a vector is a function also over independent variable t. If that is the case, then we have fti plus gtk plus gtj plus htk, where f and inside bracket t function over t, ft, gt and ht are function over t, and these are x, y and z component of the parametric vector rt. Okay, now if I differentiate it with t, then I get the gradient vector. This is what we have seen. X component of gradient vector means if fx component is ft, then df by dt, dg by dt, or dgt by dt, and dht by dt. So these are the three kind of component of the gradient vector as far as the parametric vector is concerned. So we also see that if parametric vector is like a circle, if parametric vector is a circle, parametric vector is a circle, then each point in the circle, if the center is origin, then each point is radial because it's a vector. If that is the case, then the gradient vector, the velocity vector is tangent everywhere. Okay. So what we saw is that if I have this as a circle and this is center of the circle and this is origin also, each point if in parametric vector, each point what we are addressing here is from origin, it is radial. So these are radial from the origin. So this is the vector of the each point. Now if I calculate if I do the differentiation with respect to t, the gradient vector, everywhere it is tangential. So if this is position vector, if the points on the circle is a displacement, then each point from center, it is a position vector that is radial. If that is the case, then at each point, that if that is the case, then at each point, the velocity vector or gradient vector is tangential. So if this is position vector, then velocity vector is tangential everywhere. So this is what we saw. If it is a straight line, then no problem. If it's a straight line, then gradient vector or velocity vector, acceleration vector, double derivative, all are along the line only. But if it is a curve, then the kind of velocity vector, if it is a curve, then velocity vector means gradient vector is tangential to the curve. This is what we saw. Okay, now we continued the list. So we calculate for parabola, paraboloid we could not calculate, and because we had equation in x square and y square, if someone brings equation in t, ft and gt, then probably we can calculate the gradient vector for the parabola also as far as parametric vector, gradient vector over the parametric vector is concerned. But since y equal to x square or kx square is the parabola equation, we could convert it to parametric vector, and we saw the gradient vector. So that is the another thing. And then for the circle and sphere, that anyway we saw because we know the equation. Okay, now let's move on. So now we have algebraic equation. We have algebraic equation. So if I have algebra, then we saw that if it is a parabola, we saw if it is a parabola, then our algebraic equation is set of points rather than vector. It is set of points. If this is set of points, okay, okay, if it is set of points, if it is set of points, then at each point, okay, it looks like it is very big, especially for me. So probably we'll cut it. Okay, so now if this is parabola, okay, so if this is parabola, if this is a parabola, then we saw that we have position vector along the. So if this is the point, this is the point, this is the point, and if this is origin, then position vector from origin, it is like this. Suppose that here is the origin. Suppose the origin is here, not here. Okay, origin is here, not here. Origin is somewhere here. Then position vector would be radial to the parabola all along. If that is the case, then the gradient vector would be kind of, I'm sorry. So suppose this is the, I'm actually, I started talking about the parametric vector, but anyway, so let's move on to the algebraic equation. So we have made a shift and now we are in algebraic equation. So in algebraic equation, what we saw, so we took this as origin. We took this as origin. If this is the origin, and then we have our kind of the parabola is from origin, it starts, and these are the points. The equation of the parabola is z equal to x square plus y square. Then for the calculating the gradient vector, we have the full equation x square plus y square minus z. So the gradient vector components now is 2x differentiation, 2x, 2y and minus 1. If that is the case, then if that is the case, then okay, if that is the case, then we saw, if that is the case, then we saw the, okay, if this is a parabola and these are the points of the parabola, because algebraic equation, we have set of points and then those are called independent components, and from there we get the dependent component. So if this is a x, if this is x, this is x-axis and this is y-axis, y-axis, x-axis. If that is the case, if this is x-axis and y-axis, for each x value I have y value. So this is nothing but x comma y. This is x comma y. Now we have set of x comma y in the parabola. So this is set of points. Now if I calculate the gradient vector, then if I see the x square plus y square minus z, then 2xi plus 2yj minus k is the gradient vector. So as we move along x-axis, gradient vector, the x component of gradient vector is dependent, is a function over x only. So as we go along x-axis more, the x component, that is 2x, becomes stronger. Y component 2y becomes stronger, whereas z component is always minus 1. Minus 1 means it is down, vertically down, down direction, not up direction, down direction. X is along x-axis, y is along y-axis. Now, if this is the origin, 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 this is the origin, then if I move along, if I move the point along the kind of a parabola, then at any point, whatever the x is, the x component of the vector, y component of the vector, keep growing as we grow the x, whereas z component vertically down is always minus 1. So when x and y are small, when x and y, if it origin, when x and y are small, so if I am kind of this I have taken for the parabola, means I have discussed parabola and paraboloid both. So x z equal to x square plus y square means x square plus y square minus z, that is the parabola equation. Then it is in 3D. If this is 2D, then this is 3D. If I make it wrong, this is xz plane, this is yz plane, everywhere it is parabola. So if that is the case, then if I take any point on the parabola, then the gradient vector is 2xi plus 2yj minus k. So if x is more, then gradient vector x component is 2x, powerful. Y component is 2y, powerful. But z component vertically down is minus 1 1. So if I am near the origin, then suppose I take x as tends to 0, y as tends to 0, and then z is always minus 1, means it will be vertically down. So here it will be vertically down. Can we see this? Here it is like this. The way we go up, the z component minus 1 become insignificant because x is growing and y is growing. So everywhere if I go more in x and y, it is like a flat line. The gradient is like a flat line along the x-axis and y-axis, along the xy plane. Whereas if I go near the origin, then slowly it would be kind of parallel to the z-axis, like this. Then slowly it will become parallel to the xy plane everywhere, the parabola. So it looks like the gradient vector in the algebraic form is kind of radial. Okay, if this is the origin, then if it is the direction, then it is radial. It is not like this. Can you see this? If parabolic is in parametric vector equation, paraboloid, then at this point it is tangential. Everywhere it is tangential. Whereas if it is in algebraic form, then here when x and y tend to 0, it is vertical. Vertical, not tangential. It is vertical. If it is vertical, then everywhere, can you see everywhere it is vertical actually from the surface. So if I have a paraboloid surface, then each point from the surface, it is vertical. If down the line, if it is surface is like this, then there also it is vertical. So it is always vertical everywhere. So if I have a kind of paraboloid, okay, I really have a paraboloid. So this is a kind of paraboloid. So down the line, if this is the origin, then here it is vector is like this, because x and y tends to 0 or 0, then z is minus 1. But as we go along, x is growing, and if I go along this, y is growing. If I go along this, then there is no x, only there is no x, only y. If I go like this, there is no x, only y. If I go like this, then there is no y, only x. Okay. So it is kind of in that fashion. Okay. So here it is only okay. If I take yz plane, if I take if I take yz plane, okay. So if I take yz plane, if I move in yz plane, then there is no x component. Yz plane, if this is yz plane and this is xz plane. So if I move in yz plane, then at the center it is like this, and then it will move slowly like it will become parallel to the parallel to the y-axis, because in 3D this is xy plane, this is x-axis, and this is y-axis, this is z-axis. So if this is paraboloid, then when I am at origin, then the vector equation, the equation of the paraboloid is z equal to x square plus y square. If that is the case, then it is x square plus y square minus z, for which we have to calculate the gradient vector. So it would come as 2xi, x square differentiation 2xi plus 2yj minus k. So the gradient vector x component is 2x, y component is 2y, and z component is always minus 1. So if x and y is 0, then it is minus 1. So when we are at origin, then it has only the z component, and that is minus 1. So downward. So this is the gradient vector. But if I move in xz plane, then slowly x component would catch up, and if x is more, then minus 1 of the k has no importance. So slowly it will go parallel to the x-axis, or in z plane, it will become parallel to the yz. So anywhere, if I say where x and y both are there, then it will become parallel to the x plane, xy plane, like this. Okay, so this is what we saw. So in kind of algebraic equation, the gradient vector is perpendicular. Gradient vector is kind of perpendicular to the points what we take, to the line or to the surface, something like that. But in parametric equation, it is tangential. Here it is radial. Radial in the sense from origin it crosses. Now we will see example of circle. So I have a circle. Now in algebraic equation, the formula of the circle is x square plus y square equal to r square. So if I calculate the gradient vector, it will come as 2xi plus 2yj. 2xi plus 2yj. Okay, if this is the circle, if this is a circle, this is x-axis and this is y-axis. Now, at each xy, I have the I have the point along the perimeter. Okay. Now, if I any xy, if I try to find the radial, if I try to find the gradient vector, that is 2xi plus 2yj. If that is the case, then when y is 0, then it is 2xi. If x is 1, then 2i. Means when y is 0, means along the x-axis. If it is x-axis, then at this point, the gradient vector is like this. If it is y-axis where x is 0, the gradient vector is like this. So gradient vector is again perpendicular to the line. Can we see? So now if we have parametric vector equation, r r cos theta I plus r sin theta j, then gradient vector is minus r sin theta I plus r cos theta j. If that is the case, then gradient vector is tangential everywhere, whereas the position vector, the displacement vector, is radial. Now, when we see algebraic equation x square plus y square equal to r square, then algebraic equation, a set of point we are seeing, that is along the parameter. So it is round. If it is round, then the gradient vector will be perpendicular to the round. Gradient vector for the curve, there are two kind of gradient vector. If it is a curve, then from the curve it will be perpendicular. Means whatever we are doing the differentiation would be perpendicular for the curve. If I have something and if I differentiate, the vector form will be perpendicular. If I differentiate again, then from where, if I have a and if I differentiate to get b, then b is orthogonal to a. That is differentiation. If I have c, that is differentiated from b, then b is again c is again orthogonal to b. So probably A and C would be in same direction. This is what we saw in displacement vector, velocity vector, and acceleration vector in parametric vector. So if I have a displacement vector, then velocity vector is perpendicular to the displacement, that is tangential. If I differentiate it again for the acceleration vector, then acceleration vector is again perpendicular to the velocity vector. So velocity vector, acceleration vector, and position vector, they are in the same direction but opposite. So if this is a displacement vector, then this is velocity vector, tangential and perpendicular to the position vector. Again, acceleration vector will be again 90 degree and like this. So the displacement vector and displacement vector and the acceleration vector, they are opposite to each other but in same direction. So similar to that, if I have a algebraic equation, if I have set of points that makes a line and that is round, then if I calculate the gradient vector, then it will come as perpendicular to the parameter. So it is like a radial to the circle. So 2xi plus 2yj, everywhere it is going outwards from the center. If this is the center and this is the origin, center and origin both, and x square plus y square equal to r square is the formula of the circle, then the gradient is 2xi plus 2yj. Then if y is 0, then gradient is like this. If x is 0, the gradient like this. Then everywhere it is like this. If it was a parametric vector, the gradient vector was like this. Because there was no point. Every point was a vector. Here we have points. So gradient vector has kind of 90 degree from the wherever we are calculating the gradient from differentiation. So if I go and again kind of do further differentiation, we will get those kind of scenario, 90 degree, 90 degree. Anyway, so for the circle also we have calculated the gradient vector. Let's calculate the gradient vector for a sphere. Okay, so in the name of a sphere, what I can bring? Okay, so in the name of a sphere, I believe I have a sphere. Okay, so in the name of sphere, I really have a sphere. So in the name of a sphere, I really have a sphere. So if it is a sphere, then equation of the sphere in algebraic form is x square plus y square plus z square equal to r square. So 2xi plus 2yj plus 2zk is the equation for the gradient vector. If that is the case, then what would be the scenario? Suppose that y and z is 0. Then in that case, it is 2xi. So if this is x-axis, this is y-axis, and this is z-axis, then at this point, consider it is like this, and inside this ball, the center of the ball is the origin. If that is the case, then this is the direction of the x-axis. If y and z are 0, then we are taking point along the x-axis. If that is the case, then when x, then the gradient vector is 2xi. So gradient vector is again radial here. Along y direction it is, sorry, along x-axis it is like this, and along the y-axis, okay, along x-axis it is like this. Then if it is along x-axis it is like this, then along the y-axis it is like this, along the z-axis it is like this. So now looks like that it is radial, it is kind of perpendicular to the surface, not tangential to the surface, perpendicular to the surface. Now if I am at origin, then it is away from the origin, perpendicular to the surface everywhere. This is this is gradient vector. This is not gradient surface. There is another thing called gradient surface. Like if I have a equation like x square plus y square plus z square equal to r square, and then I have a formula in z equal to r square minus z equal to r square minus x square minus y square. If I calculate the partial derivative, then z is equal to square root of r square minus x square minus y square. If I calculate the partial derivative along x-axis, that is dz by dx, partial derivative along y-axis, that is dz by dy, and if I have dz by dx, dz by dy, and then if I get a surface, that equation of the surface is gxy equal to dz by dxx plus dz by dyy hxy. We have fxy equal to a square root of r square minus x square minus y square. Z equal to a square root of r square minus x square minus y square. If that is the case, then I can have at any point x comma y, I can have an equation of the surface, that is gxy, that is dz by dxx plus dz by dyy. That is called the surface of tangent. That is gradient surface, not gradient vector. So if I have a if I have a parabola, if I have a parabola, then the gradient surface is like this. This is gradient surface. This is gradient at any point. But if I talk about the gradient vector, then it is radial, not like this. Radial everything. So gradient vector and gradient surface are two different things. Gradient line and gradient vector are two different. If I have 2D item fxy function over x, then I have tangential line and tangential line or gradient line, or I will have gradient vector, that is both are two different. So if there is a curve like this, then tangential or gradient line is like this, tangential vector is perpendicular to it. If there is a 3D shape and there is a curve like this, then tangential surface, now tangential surface everywhere it will be like this, tangential surface or gradient surface. Whereas the gradient line will not be like this, it will be perpendicular everywhere. So that is the gradient vector scenario in algebra itself. So when algebra we have set of points and it constitute a 3D shape, then gradient vector at each point is radial, perpendicular. Okay, but if this surface is described in parametric vector form, then gradient vector is tangential. This is what we saw. But idea is whatever the equation we are taking, gradient vector would be perpendicular. If I take set of points, then it will be kind of at each point it will be tangential. But if I take gradient vector, not the point, then gradient vector itself is radial. This is gradient vector. I'm sorry, if I take parametric vector, then algebraic is set of points, whereas parametric vector is radial. At each point, I have a radial vector. If parametric vector itself is radial, then the gradient vector would be perpendicular to this with tangential. Okay, So we consider like that algebraic equation, the points what we are taking, okay, the points what we are taking. So it's like it's like a tangential, means each point we are taking here and there. So it's like a tangential everywhere, touching the surface. So the gradient vector will be perpendicular to it. Whereas in parametric equation, parametric vector, each point is kind of radial. So the gradient vector will be tangential. So other way. Now, which form is better? Wherever you find the solution. If you think that you should proceed through the algebraic way, then this is how it is. If you think that I should proceed through the parametric vector way, then this is how it is. Okay, so which way you are proceeding, that way you have to pick up, and that is the grammar and that is the language. So that is the science of the gradient vector, both in parametric vector and algebraic equation. What is the importance of gradient vector? Okay, what is gradient vector? So when we have seen the parametric vector, we brought a term called vector field. Vector field is nothing but it's a differentiation over the algebraic equation, partial derivative. The if I have a vector field, a field which is a vector field is generally it has x component. Since it is a vector, it has x component, y component, and z component. Rather than saying x component, y component, z component, if vector field has nomenclature as capital F, not a small f. So vector field is capital F. So if I have an algebraic function small f, then gradient vector is capital F. Or we can also say inverse delta, not delta, inverse delta of the f, or just grad f, whatever we can write, grad f, inverse delta of f, or capital F. So when we write capital F, then it becomes like a vector field. If it is a vector field, capital F, then it has component like f1, f2, f3, f1i, f2j, and f3k. Now f1, f2, f3 each are function over xyz again. So now because if I to get f1, I have to differentiate the algebraic equation small f with respect to x. If I differentiate with x, certainly there may be y and z there also. If I differentiate with y to get the f2 and differentiate with f3, suddenly x, z, and xy, these components will be there everywhere. So f1 in the vector field is function over x, y, z. f2 and f3 all are function over x, y, z. Now, if I have a vector field also sometimes we call it as velocity vector. So at each point, at each x, comma, y, comma, z, it produces a vector. Okay, vector field is a vector factory where if I try to find the vector field at each x, comma, y everywhere, it gives me a vector. Because f1 will give for each x, y, z, it will give a scalar. f2 will give a scalar, f3 will give a scalar. A scalar I plus a scalar j plus a scalar 3 happens to be a vector 1. So vector field at each unique x, comma, y, comma, z would lead in a vector, in a scalar way. So vector field produces vector factor. Now situation comes that y vector field or gradient vector is important. Why it is important? A simple, we'll see this in a line vector. But consider a case that I have a algebraic equation and the algebraic equation where there is no I, j and k, simple algebraic equation in function of x, y, z. If I do the partial derivation along x-axis, y-axis and z-axis to get the a vector that has x and y and z component, that is called gradient vector or vector field. Now, if I have a gradient vector or vector field, so consider that is a kind of some force, and someone is moving in the force. Like like there is a wind that is flowing from, this is east. So from east, to west. One wind is flowing from east to west. So there is a force in the wind. So force is from east to west. Is running. A person is running from south to north. Okay. How much is the work done that is seen on the person by the air? Okay. So work done is nothing but force into displacement. So force in the direction of displacement. So if person is moving from south to north and force is from east to west, then we have to get the dot product of two vectors. And then there the if I have algebraic equation and if I differentiate, then I get the force equation. The force into displacement, I get the work done. So work done is 0 because it is 90 degrees. But if I move west to east, when air is east to west, then certainly the work done by the air on that person is negative because it is not assisting the person, it is resisting the person. If person is moving from east to west and direction is same, then it is assisting the person. So work done on the air on the person is positive. But if person is moving somewhere haphazard like this, then at each point the work done by the force of that person is delta movement dot the force vector and the direction at that point, direction vector and force vector at that point. If we do the dot product and do the integration, then we get the work done at each point differently. If it is moving like this, the person is moving like this. But anyway, if person is moving in a way that it is going like this, and he is coming back to his original position. Person is moving from here, it started moving. Okay, now consider this is south and this is north, this is east and this is west, this is south and this is north. Person from south, he started moving like this, went to north, and then slowly he came back to same position. So net displacement he made is 0. This is called kind of closed path. If he is moving in a closed path, is moving in a closed path, and the force of the wind is gradient vector. It has some algebraic equation. Through the partial derivative we calculated the gradient vector. If force of the wind is a gradient vector, mind it is a gradient vector. If it is a gradient vector, then if I do the integration, it will come back to the original algebraic equation. If a gradient vector f1, f2, f3, f1 if I integrate with dx, f2 if I integrate with dy, and f3 if I integrate with dz, and it comes back to the algebraic equation, then it is considered as a kind of we'll see this. Okay, so it is considered as a separate kind of gradient wave. So if this is the, this is considered as really as a vector. If I have a wind force, and wind force is in a form of vector field. Vector field means it is in a form of ijk, where f1, f2, f3 are function of x, y, z. So if wind is flowing, and wind is flowing in a way that the force of the wind is a vector field. If it is a gradient field means if I integrate and get back the algebraic equation, not all vector fields are, if I integrate f1, f2, f3 with the respective of dx, dy, dz, then it will lead to algebraic equation. May not be possible. But if the vector field, the force what we have the equation in a vector field in x, y, z, if it brings the algebraic equation back, then that vector field is called gradient vector. If gradient vector is there, then person is moving in a closed region, then net integration, net work calculation is 0. That much gradient vector is important. If you have a wind force, and wind force is a vector field which has equation in f1, f2, f3, f1i plus f2j plus f3k, where f1, f2 each are maybe a function of x, y, z separately, then this is a vector field. If this vector field is not a gradient, if I integrate f1, f2, f3 separately with the dx, dy, dz to get the algebraic equation, if that is not happening, then in a closed loop, if I do the line integral force into displacement to get the work done, then it is not may not be 0. But if vector field, that is a wind is flowing, the force in the wind, if I describe it as a vector field F1i plus F2j plus F3k, and from the vector field, if I integrate with the dx, dy, dz for the F1, F2, F3, and it comes as an algebraic equation, then it is called a gradient vector. That vector field comes as a gradient vector, because gradient vector can be converted to algebraic equation as far as integration is concerned. Because gradient vector came because we did the partial derivative of the algebraic equation. If that is the case, then in that vector field, if I start from the beginning and come back again to the starting point, and if I do the integral, means if it is a force field, then if I do the integral, in the sense if I calculate the work done, then in the closed loop it is zero. So gradient vector can have many other importance. Gradient vector, after all, it talks about the rate of change in along the x-axis, along the y-axis, and along the z-axis. Rate of change is big thing. If I have rate of change along y-axis is high, then a small variation in x brings high value of y change. If I have dz by dx, dz by dy, both are very high, this proves that rate of change, this proves the parabola, if I am taking the paraboloid, then a small change in x brings high change in z. So it is sharp like this. If parabola is slowly it is growing, means more change in x brings less change in z. More change in y brings less change in z. So if I see the gradient vector, immediately I can find that what is the shape of the parabola, because rate of change along x-axis and y-axis I am knowing. So the equation, if I take the parametric equation of the parabola, then the parametric vector and the kind of gradient vector, they are orthogonal to each other. So their dot product is anyway there, zero. So we got talking about the gradient vector closed loop. So if closed loop is circular, then anyway we saw they are tangent, they are perpendicular to each other. So if I have a wind, that is a equation is circular. If I have a wind that is a gradient vector and loop is circular, then anyway if I calculate the work, then gradient vector dot the line vector. So anyway every point it is 90 degrees. So anyway it is 0. So means we know that gradient vector is the rate of change, and it will be orthogonal to the equation we are calculating the rate of change. Then we can have so many things that will be in the consider. So we close the discussion on the gradient vector, and we saw the parametric vector gradient vector and algebraic equation gradient vector. So in algebraic equation, gradient vector is radial, whereas in parametric vector the gradient vector is kind of tangential. This is what we saw. Gradient vector, since it is perpendicular to the whatever we are calculating, if I calculate the line integral of the gradient vector in a closed loop, it comes to 0. So many things we can kind of get from the gradient vector. So all about the gradient.